Hello, everyone. So we move on to study lecture 4 of module 4. Module 4 is about the robot control. In lecture 1, we have studied the control technique in control theory. We have a study 1 technique in time domain and 4 technique in frequency domain. In lecture 2, we have studied the dynamic equation of a robot under control, which include 3 relationships. The first relationship is at the input of a link joint. The second relationship is as an input of a top joint. And the third relationship is at the input of a power joint. In lecture 3, we have studied the concept of a transfer function and the block diagram. Then we have applied these two knowledge to come out the block diagram of a robot under control. In this way, we have a better understanding about the inner structure of a robot under control. Now we are ready to design control system for robot. And there are two approach or two scenario for us to implement control system for robot. One is to do the design of a robot's control system in joint space. And the other scenario is to do control system design in task space. Today's lecture is for us to study the basic design method in joint space. Before we enter the study of lecture 4, it is always good to remind you about the learning objective, which is to make you to become a designer of a robot as a product. By now, you should know that there are many generalized users in manufacturing and in society. Among these generalized users, they are generalized need, which is to have a motion provider. And robots are very good candidate to serve as a motion provider. And from the study of module 1, so you understand motion could be described by equation of a trajectory of some important motion coordinate, such as X, Y, Z, and theta. For mobile base, the two important motion coordinate will be circular velocity of the left view and the circular velocity of the right view. All right. Therefore, your focus should be on the answer to question 3 and question 4. All right. And this slide gives you the general answer to question number 3. And this gives you a generic blueprint of a robot that you may design in future. From this blueprint, you can identify the presence of a module 1, the presence of a module 2, the presence of a module 4, and also the presence of module 3, right? So module 1 will enable you to design robot software, right? And in future, you can extend this robot software to include robot intelligence. And this is a very, very big topic, all right? Module 2 will enable you to design robot's body in terms of mechanism, actuator, sensor, and controller. And module 4 will enable you to design robot's control system, because robot is a motion provider. The motion performed by robot could be programmable and reprogrammable. All right. Module 3 will enable you to design digital twin of your robot or simulator or simulation of your robot. So therefore, with the presence of these 4 modules, you should be able to come out very comprehensive blueprint of your future robot. And in order for you to draft out the detail of this generic blueprint, you need to learn all this knowledge, which have been categorized into 4 modules. So you see you have the module 1, module 2, module 3, and then module 4. Today we are still in the study of module 4, right? So now we enter the study of lecture 4 of module 4. And today's lecture will follow this outline. So let us begin with the concept of a joint space, because some of you may ask this question, what do we mean by joint space? All right. So first, we look at the nature of our robot. So this slide shows you the hardware detail based on the study of a module 2. Then you should be able to understand this slide. In the design of a robotic joint, so you understand in general, a robotic joint will consist of 3 joints. So we have a link joint, top joint, and the power joint. Power joint means actuator or motor, okay? So in general, a robotic arm may have n degree of freedom. N could be equal to 6 or equal to 4 or equal to 2, etc. Okay, and for each joint, we must have a control signal and the flow of electric energy to enter the power joint. Then power joint will convert electric energy into mechanical energy. Then mechanic energy will be converted into motion. All right. So therefore, the robot's brain must have this capability to control in parallel at the least n power joint. So n could be equal to 6 or equal to 40, 20 if we talk about the humanoid robot, right? So this is the hardware capability. Then for each control signal, there must be a power amplifier in order to release electric energy to the dedicated power joint. Okay, so this slide highlights to you the hardware detail of robot. Then the software detail basically correspond to the blueprint of your robot, okay? And on top of the software, you see the presence of hardware is here, because hardware basically just to perform the motion. And behind the control system, you will also see the presence of a hardware. So that means on top of the blueprint, so at the highest level of the blueprint, we have this functional diagram, right? So this gives you the software details. So we must have a module which will undertake planning for task, for action, for motion, for path, for trajectory. We must have a module which allow us to, or allow robot to undertake inverse kinematics computation, forward kinematics computation. you must also have a software module which will handle the control aspect inside your robot. All right. Then, based on this blueprint, so you see we have a motion coordinate, which make use of X, Y, Z, theta X, theta Y, theta Z. So these are the coordinate in the global coordinate system. Okay, so these are rotation angle about the three principal axes of the global coordinate system, right? And here we have a motion coordinate for each individual joint inside your robot. So you have a theta Y all the way to theta N. Therefore, this motion coordinate actually define another space which is different from this space. Okay, so we will call this space as a task space. This is a three-dimensional physical space in which we are living in. All right, so we call this space as a task space. Then this space is different from this one. Then we call it as a joint space, right? Because most of this or all of this variable or coordinate refers to the angular position of the joint inside the robot, all right? So this is a definition of a joint space. Now you may ask this question, okay, the output from module 1 are the motion equation in task space. How do we know motion equation in joint space? The answer will be inverse kinematics, all right? Then you may ask another question. If I know, okay, the input motion to robot mechanism, okay, in joint space. So these are the input motion to robot mechanism. How do I know the output motion from robot mechanism in task space? The answer is what? Forward kinematics. All right, and all these equations for kinematics have been studied by you in module 3. Then here I just give you two examples. One is to illustrate, okay, the idea or the procedure of doing inverse kinematics, and the second example to show you the concept of forward kinematics. Okay, so in this lecture I will show you two very simple examples. The purpose is just to refresh your memory about the inverse kinematics and the forward kinematics. All right. So this example show you a specific solution to inverse kinematics. Inverse kinematics means we have a desired output from robot mechanism. What should be the desired input to the robot mechanism? For example, in this case, we have a scalar robot. The first two links of a scalar robot are parallel, okay, in the horizontal plane, and therefore, so the link 1, link 2 will change the XY coordinate of the two tips at this robot. So XY, these are the XYZ are desired input motion to this robot. Then from XY, then how to determine the desired angular position of joint 1, angular position of joint 2. Okay, so then I redraw, okay, this robot graphically in this way. Then you will have a better understanding about the relationship between the output motion from the mechanism and input motion at the joint. Okay, so here we have a link 1, link 2, and the link 1, link 2 will allow us to perform output motion described by xt, yt, because the z does not depend on link 1, link 2. All right, so z only will dictate the motion of link 3. All right, so here we only focus on the desired output motion xt, yt. All right, so we first do a quick analysis about the question in order to come out with some key relevant information. So by default, we assume that the theta 1 equal to 0, theta 2 equal to 0, and the link length of link 1 equal to L1, link length of link 2 equal to L2, and the joint 1 is at the position O1, and the O2 represents the position of joint 2, O3 represents the position of joint 3, all right? Then when we have a desired output motion, for example, xt, yt, then we want to know what should be the desired input motion, theta 1 and the theta 2, okay? So if the robot can produce a desired input, theta 1, theta 2, then we will obtain desired output motion, xt, yt, all right? So you see this relationship, okay? So this is a typical scenario of inverse kinematics, all right? And of course, this is a very simple case, then solution is quite straightforward because if we link O1, O2, O3 together, we have a triangle, then we can apply this cosine theorem, okay? Cosine theorem tells us these three equations. For example, cosine alpha is equal to L1 square minus L2 square, L1 square plus L2 square minus L square divided by 2 L1, L2. And cosine beta equal to L1 square plus L square minus L2 square divided by 2 L1, L. Then cosine sigma equal to L square plus L2 square minus L1 square divided by 2L and L2, all right? Then if we want to know what is alpha, then obviously alpha is equal to arc cosine L1 square plus L2 square minus L square divided by 2 L1, L2, okay? If we want to know what is the beta, then beta equal to alpha, arc cosine, okay, with a ratio between L1 square plus L square minus L2 square divided by 2 L1, L, all right? Once we know alpha, beta, then what is theta 1? Theta 1 is equal to beta plus phi. Then what is this phi? Phi is equal to, because the tension phi equal to y over x, then phi equal to arc tension y over x. Then what is L? Because we know the link length of link 1, link length of link 2, then what is this L? This L, basically, you look at this triangle. So L is equal to square root x squared plus y squared, square root x squared plus y squared. So you see, we have the full set of equation for us to determine the input motion to this robot mechanism from the knowledge about the output motion, right? So this is a typical scenario of making use of inverse kinematics to determine the value in joint space from the knowledge of coordinate in task space, all right? So now you understand what is joint space, all right? Now we look at the detail of designing control system in joint space. Then first thing for us to know will be the input, second thing will be the output, and the third thing will be inner process, which will produce output from the input. In control theory, control input means desired output. So desired output, okay? So then, okay, based on this blueprint of your robot, then immediately you understand, okay? So this is a control loop. What should be the input to the control loop? So input to the control loop come from motion equation in joint space. Then the answer will be this one, okay? So these are the controllable variable in joint space, okay? So here we can specify the desired output. Then after the control, then the actual output will be exactly equal to the desired output. Since this motion are required by the task. If the robot can deliver this motion, so it means what? Robot can perform a task. Okay, so now you understand the philosophy behind the operation of a robot. Okay, so a robot could perform a motion, then through motion execution, robot will be able to perform a task. Okay, so let you see this outer loop, you see. Okay, so here you have an inner loop. Then you just imagine that we have this outer loop. Okay. Then, okay, in general, the motion coordinate in joint space will involve angular position, angular velocity, angular acceleration. Then you understand acceleration are related to mechanical energy for angular motion, angular acceleration are related to torque. For linear motion, linear acceleration are related to force. All right, so these are three types of controllable variable in joint space: angular position, angular velocity, torque. Okay, torque is basically is related to acceleration. All right. Now I use this second example because here you may know, okay, how to obtain this desired output. So this is control input. Control input also means desired output. How to obtain this desired output? Then answer is what? Robot kinematics. Now I'm going to show you an example which will help you to understand forward kinematics and the inverse kinematics. Okay. For example, here we have a robot base with differential view drive mechanism. So you understand when the left view's velocity equal to the right view velocity, then this robot base will move straight. Okay. When the velocity in the right view is bigger than the velocity in the left view, then this robot will rotate. When this rotate, it means what? The body of the robot will have an angular velocity plus a circular velocity, right? And in this case, is a typical example. So the robot will rotate about the axis which pass through the center of the robot. Okay, if the velocity of these two views are equal in magnitude but opposite in direction, equal in magnitude, opposite in direction, then this space will undergo a pure rotation. Then immediately you understand there is angular velocity, okay, produced on the body of the robot. And from this illustration, you can imagine, okay, L, let's say, the angular velocity of left view or circular velocity of the left view will contribute to the angular velocity of the mobile base. And for the right view, the circular velocity of the right view or angular velocity of the right view will also contribute to the creation of circular velocity by the mobile base in the counterclockwise direction. So both of them contribute to the angular velocity of the mobile base in the same direction. So therefore, the mobile base angular velocity should be a function of angular velocity by left view and angular velocity by right view. Okay, so if we know angular velocity of left view and the right view, then what should be the angular velocity of the mobile base? So this is a typical example of forward kinematics. So it means I know the motion of left view, I know the motion of the right view. Then what will be the motion of the mobile base? So this is a typical scenario of forward kinematics. All right, but of course, once you know forward kinematics, you can also derive inverse kinematics. Okay, so here you must pay attention to the meaning of this variable when you talk about the angular velocity of the two view. So it means this view rotate about its own axis. Okay, this view rotate about its own axis. When we talk about the angular velocity of a mobile base, so it means the rotation of the mobile base about the vertical axis, which is perpendicular to the screen. Okay, it may pass through here or pass through somewhere here. This is the center of the circular path followed by the mobile base. All right, so pay attention to the meaning between these two types of angular position. Okay, then this will help you understand the meaning of the forward kinematics. Okay, then when the view rotates, okay, and assume there's no slipping between the view and the ground, then it means what? Then the axis of rotation of the view will have circular velocity or linear velocity, okay? And this circular velocity, linear velocity is equal to the circular velocity on top of the view, all right? So circular velocity of the two view, this could refer to the circular velocity at the center of the view or at the top of the view. So they are equal, okay? So this circular velocity are due to view's angular velocity, all right? So then we also have a circular velocity of the two view, okay? This for you to understand. So then this circular velocity of the two view actually will create robust angular velocity. So if they are not equal, then here you have a circular velocity, here you have another circular velocity. Then these two circular velocity will create the circular velocity of the robot and the angular velocity of the robot. So try to understand the causality among all these motion coordinates, all right? Then we look at the solution, and I hope that this equation will help you to better understand the physical meaning, okay, involved in the analysis of mobile robots motion, okay? For example, if let's say we look at the left view, then the motor inside the left view will output a torque, which will drive the axis of a left view. So then this torque, if you apply like Newton's second law, then this torque will produce angular acceleration by this moment of inertia, okay? The moment of inertia of the view, so you can calculate by choosing this solution. So here I give you this short table, and then in this case, view is behave like a ring, okay? So this is a ring, rotate about this axis, the moment of inertia is equal to m times r square, okay? So m times rl square, okay? And when there is no slipping, okay? So then the view will move forward. Then you can imagine, okay, this view actually receive a pushing force, and this pushing force come from a torque, okay? And then relationship is tau divided by the moment arm. Because when this rotate, you just imagine you have this okay, frictional force, static friction force. Okay, so it resists, okay, to resist it, resist to the clockwise rotation by the view. Then this resistive force actually is this one. So you will push the view to move forward. Okay, because when you rotate in this way, then the ground. So this force actually comes from the ground. Okay, due to static friction. Okay, so assume that static friction is strong enough, which will prevent the view to slip. Okay, so once you have this, then subsequently, then you know, okay, because here we have an angular velocity will have a circular velocity either on top of the view or at the center of the body of the view. So you see, just imagine you have this one. Okay, so this is the circular velocity of a left view. Okay, then relationship between circular velocity of the left view and the angular velocity of the left view is by this. All right. Then for right view, you have a similar or same set of equation. All right. Okay. Then with this background knowledge, then immediately you know, okay, circular velocity of the left view, circular velocity of the right view will make the robot body to rotate. Okay, so if we consider the motion within the local coordinate system assigned to the robot body, so then about the axis which pass through point A, then you will see VL divided by R. R is, in this case, is this distance from A to the center of the view, which is equal to half of L. Then VL divided by okay. So we consider, okay, because VL and the VR will move together. Then in this case, we treat as a MIMO system. Then MIMO system, then in this case, is equal to the sum of the two SISO system. Okay, first SISO system means the absence of a VR. That means the VR never move. Okay, we only have a VL. Then in this case, the radian of rotation, then this will make the mobile robot to rotate about the axis which will pass through this point. Then the angular velocity will be equal to VL divided by the width of the mobile robot, is this one. Okay. Then for second, the SISO system is the case in which there's absence. That means VL equal to 0. Then we only have a VR. Then VR will produce angular velocity, which is equal to VL divided by the radian. So radian is L. So then you have a second term. Because the VR will make the mobile base to undergo counterclockwise rotation. This one will make the mobile base to undertake clockwise rotation. Then the sum, that means this one minus this one, then should be equal to the angular velocity of the mobile base. All right. So this is a kind of forward kinematics. It's a typical example of a kinematics, forward kinematics. Okay. So this is the result about the angular velocity. Then how's about the circular velocity? Because now we can imagine, okay, so assume that this robot undergo perfect motion, there's no slipping, okay? When this mobile base rotate, follow circular paths, the center of all these circular paths are at the same point, B, for example, because when this rotate, left view will follow circular paths, right view will follow circular paths, center of the robot will follow circular paths. Assume this is the perfect motion. Then all these three circular paths will have a common center of a circle, which is B. Then with respect to the point B, then you can imagine, okay, the whole rigid body rotate about the axis which pass through point B. Then this rotation, which is the omega R, will produce circular velocity of the right view, circular velocity of the robot's center, and the circular velocity will at the view, okay, left view. Therefore, if A is in the middle between left view and the right view, then VR is equal to VL plus VR divided by 2, because it's also in the midway, so it's equal to the average between VL and the VR. Okay, so this is the second forward kinematic equation. So these are the input motion from robot's mechanism. Then this is the output motion in terms of circular velocity of the body. And this is the input motion, and this is the output motion in terms of angular velocity of the robot's mobile base. All right. Then from these two, then we can also, okay, write down this equation. Okay. So okay, this means this angular velocity, okay, is also, the interpretation is when we, okay, use this axis of rotation as a reference. So then it means what? So angular velocity, omega capital R, about the axis passing through B, okay, is related to VR, is also related to V capital R. So then what is the relationship between omega R with respect to the capital R? Answer is what? Should be omega, should be V capital R divided by radian, is this one. All right. So then if we try to find out the relationship between VR and omega R with respect to this rotation axis, which pass through point B. Then what is the relationship? Then the relationship should be this one. So it's a VR small r divided by radian. So radian is equal to capital R minus the half of L. Okay, so you have this. So you have this equality. Okay, then for left view is the same. Okay, then what will be the relationship between VL and the WR? Okay, so then in this case, so VL divided by this radian is equal to R plus half of L. Okay, so then you have this equality. Okay, so based on this equality, then you can find the inverse kinematics, because this is the output motion, this is the input motion. Okay, and also this is the input motion. Then you have a solution for inverse kinematics. Then for this one, you may find the second inverse kinematics equation, which calculate the input motion VR as a function of output motion W capital R, V capital R. Okay, so you just reformulate a little bit this equation, then you should be able to get these two equation of inverse kinematics. So you see the input motion as a function of a circular velocity of a mobile base, angular velocity of a mobile base. These two are the output motion from the mobile base, and these two are dictated by the result of module 1. Okay, so we have a task. From the task, then we can determine what should be the trajectory followed by the mobile base. Therefore, along this trajectory, we can determine omega capital R and V capital R. All right. And the second inverse kinematic equation will be this one. Okay. So this is the circular velocity at the right view, which will be the function of circular velocity of the mobile base and angular velocity of the mobile base. Okay. Once you know circular velocity of the left view, circular velocity of the right view, then we can calculate what is the angular velocity of left view, angular velocity of the right view. Then this will be the input to the control system for these two motors placed inside left view and the right view. All right. So this will be the control input or desired output. Okay. So now we move on to see then how to construct the closed loop feedback control system. Then we need to know how to obtain the sensory feedback in order to have a negative feedback plunge inside the control system. Okay, so here we want to know, are we able to measure the angular position of a link joint or power joint and torque joint, etc. Okay, so here we have a power joint, we have a link joint, and in between that we also have a torque joint. Okay, so this will be the sensory output from the measurement at the shaft of link joint, torque joint, and the power joint. All right, so this will also be observable variable. So these are the technical terms in control theory. So basically it means, are we able to measure this variable? If we are not able to measure this variable, then we cannot close the control loop. All right, so this is mean. So we want to know, so inside the robot, are we able to measure angular position, angular velocity, and the torque? So the answer should be yes. All right, okay. So once we are able to measure all these motion coordinate in joint space, then we can design the control system and do the testing. So this video show you the result of joint space control.
Even this kind of thing. Okay. It's a very odd shape one. Like that way. And skill box. And stuff like that. So, 한번 다시 잡을래요? You may feel some graving force. Just try to. Yeah, I will show you. Okay. It's different moves, so here's okay. Now it's the handshake move.
The tracing is right hand.
Yeah, and if you put your palm like this way, it will grab. Okay, would you try? Anybody will try? You just take your palm like this way and just wait. Okay. Yeah, naturally. Try to move up and down, just slowly. Okay. There's a full stop sensor here, so you just follow your movement. Very natural, right? Okay, try. Yeah, go here. Yeah. How do you feel? It's very simple.
Yeah, it's not so hard.
Yeah.
Try to follow.
Because you naturally make the form according to the shape. Yeah, okay, that's perfect. This figure is missed. Okay, yeah. They naturally dress.
Right. So then next question will be, okay, how to design the closed loop control system based on the available knowledge about the input, about the output, about the capability to do the measurement of controllable variable. Okay, so is it just close a loop? Okay, then calculate the difference between desired output and the actual output, then lay it down. Okay, so actually it's more than that, because we may have these two scenarios. First scenario is about the knowledge of dynamics under control of your robot. And the second scenario is about the absence of the knowledge about dynamics of your robot. And the first scenario corresponds to the case in which you have a digital twin of your physical robot. Therefore, you know exact mathematical equation. Then how to make use of this knowledge to come out more sophisticated control loop. Okay, so that is the question. And the second case corresponds to the situation in which we just have a rough understanding about the dynamic model of your robot. Then in this case, how to achieve accurate control of your robot. Okay, so we are going to study solution which correspond to these two situations. Then let's begin with the first scenario in which you have a perfect digital twin for your physical robot. So it means what? You have a perfect knowledge about the dynamic model of your robot. Then in this case, we should be able to leverage on the availability of this perfect knowledge, okay, in order to come out a better block diagram of feedback control system for your robot. All right. So assume you have a digital twin of your physical robot. So it means what? It means you have a perfect equation of dynamics. Therefore, inside the mind or inside the computer, inside the mind operating system of your robot, then we should be able to compute the desired motion, okay, based on the assigned job or assigned task, okay. Then with this desired motion inside the mind of your robot, then we should be able to calculate. Okay, so you remember this is the equation that we have a study in lecture 3, all right? So then we should be able to compute what should be the desired value for top, okay? So all these calculations occur inside the mind of your robot or occur inside the digital twin of your robot, all right? So you calculate all this, and also the digital twin of your robot should be able to calculate the desired value for D. All right, so then we can draft out the pseudo block diagram because strictly speaking, the block diagram must be a signal flow in frequency domain. but we just borrow the idea of a block diagram for us to have a better understanding of a signal flow in time domain. Okay, so you treat it as a signal flow in time domain, right? But borrow the concept of block diagram in frequency domain, all right? So therefore, you see, then once we have a this signal times this transfer function, then you will get this term, okay? Then for this one is the sum of these three terms. If we have a this signal times this one is here, okay? So this one times this one will get you this first term. Then this signal times this transfer function will get you the produce a second term. Then for this one, it means the position this signal, okay, times this transfer function will produce a third term. Now we add them together, okay? Then we will have this signal. Then these two signal A together, then result will be desired the top, all right? And we have also studied this equation in lecture 3. Then from this dynamic equation, then we can obtain this result. We express the control signal as a function of the top and the function of angular velocity, all right? So both sides divided by this, then shift this to the left-hand side, then we swap the equality, then you get this result. So it's quite straightforward. Then we can also draw the block diagram. But in this case, since we have a Laplace transform, then this will be the block diagram. Okay, so this one times this transfer function will give you first term. Then this one times this transfer function will give you the second term. Add them together, then you get the signal in frequency domain, which is about the control signal, which is the output from robot's brain. All right. Now we can put them together. Okay. So it means we can determine the desired control signal from the desired motion and the input to your robot. All right. Because we can connect this one to here, and this can be provided by this one. Okay, so we just draw it in this way. Then you see the Q dot is here. Okay, so then we have this block diagram. Okay, which relay desire the motion to desire the control signal. So all these things occur inside your robot's brain or occur inside the digital twin of your physical robot. And then we can lump all this into a black box. So you see, we have a desired velocity as the input, then we can produce desired control signal inside the mind of your robot. All right. Then you can make this expectation. You may expect that if we supply this value provided by the digital twin of your robot to the physical robot, then let the physical robot take this as an input. If everything is perfect, then your physical robot may produce a motion which will be exactly equal to the motion at the input side. Okay, so then this gives us an advantage, okay, of achieving the control result in a single step of computation, because this computation can be undertaken in a fraction of a second. We just turn on this signal, then instantly you may see this motion appear in the output of the physical robot. So you see left-hand side is a digital twin of your physical robot. Right-hand side is a physical robot. So you let these two work together, then you can achieve this magic result channel. Okay. However, in practice, okay, you may not be able to have exact value for all these metrics. Then at the least you can expect that the output motion from a physical robot should be very close to the input motion to the digital twin. Therefore, this is also very useful structure inside the design of a control system. Then we can still add in negative feedback here to minimize the residue due to the error, then make the final error to become 0. Then in this way, we can come out the least block diagram for the control of a robot if we know the dynamics equation of the robot. Okay, and this slide basically is just to simplify the notation because if we draw this block diagram with the entire detail of your physical robot, this is a physical robot, and this is your digital twin. Okay, so and here we just this is your digital twin of a physical robot. Then we use this black box to have a simple representation. For the physical robot, is the same. Okay, so we use this black box to represent the dynamics of your physical robot. Therefore, from here, you see we have a simple representation. Left-hand side is the dynamics of the digital twin. Right-hand side is the dynamics of your physical robot. Okay, if they cannot work perfectly, but you should not worry because we can still, design a negative feedback loop here. Okay, so we have a sensory feedback. We still have a controller, which will make this error to be 0. Okay, then in this case, the output could be one of these, could be position, velocity, and acceleration. All right, and this is because inside our robot, normally we have this sensor, velocity sensor. This sensor allow us to obtain position information. And if you know velocity, if you compute first order derivatives, you know acceleration also. All right, so it means in general, these motion value are available, for the design of a control system. All right. So then with this control scheme, because this is very efficient, this one will shorten response time and improve response accuracy, because here we use the digital twin of your physical robot. If the dynamic model is very, very close to the dynamic model of the physical robot, then this signal will help us, or help your physical robot to reach the desired output within a very short period of time. All right. So here, then you should be able, to this type of behavior from the robot. So you see, all these motion are controlled by robot control system. Okay. So all these are controlled motion. Okay, so it's quite impressive. All right. Then we try to look the way to design control system for the second scenario, in which we know nothing about the robot dynamics, or we intentionally do not want to consider the dynamics of a robot under control. So this may correspond to these two situations. We do not want to consider, the dynamic equation of a robot, or we do not have a dynamic equation of a robot under control. Then in this case, what should be our design solution? So, and then in this case, we try to make a robotic arm to become LTI system. Then in this way, then MIMO system will become SISO, sum of a SISO system. So we try to achieve this result. Because this result will be very interesting. Then we can do independent control of all the actuator inside your robot. Once we do independent control of all the actuator inside the robot, then the complexity of a control become the simplicity of controlling a single motor. Then we know how to control a single motor. Therefore, we know how to implement the overall control system inside the robot. All right. So this will link you to the study of lecture 1 in module 4, because in lecture 1 of module 4, we know how to control an individual motor. All right. Okay. So we start with this block diagram of robot dynamics under control. Okay, so now we make an assumption about the absence of knowledge about this dynamic equation, or intentionally we do not want to use it. Okay, then in this case we try to simplify this block diagram to see whether could we make a robot arm to behave like an LTI system, all right? So if you observe carefully, here you see inverse of KR, inverse of a KR, because inside the KR, we have a, this is a diagonal matrix with a reduction ratio. If during the design, we choose torque joint or speed reducer with a high reduction ratio, for example, 200. So then you see 1 over 200 times 1 over 200, then that is equal to 40,000, 1 over 40,000, okay? So then this is a very big divider. Then eventually you can imagine this signal will be extremely weak. So very, very weak signal here, very, very weak signal here. If you add them together, then this is also very, very weak signal. So it means what? We could ignore all this, this transfer function and treat this one as a disturbances, all right? And in the study of lecture 1 of module 4, so you remember we have one example in which we choose a PD controller here. With the PD controller here, these disturbances will never produce any steady state response in the output. So it means the PD controller could completely cancel out the presence of this signal. All right. So then these two considerations lead us to simplify this block diagram in this way. Just treat this one as noise disturbances. Okay. Therefore, then we will see this block diagram. So it will become MIMO system, and will also become a LTI system. Okay, for LTI's MIMO, the result is sum of SISO. Okay, pay attention. So this result is only valid with the LTI system. If your system is not LTI, then you cannot do this, make this assumption, okay, or equality. So, all right. So with this consideration, then your robot, the good news is your robot become an LTI system. Then you can apply this property of LTI system. Okay. Then how do we achieve this result? Answer is what? Okay, at the module 2, when you design your robot body, try to choose a torque joint with a very, very high reduction ratio. All right. So this is the only condition for you to consider when you do the design of your robot's mechanic system. And therefore you understand speed reducer are very, very important in industrial robotics, okay? Because through this speed reducer with a high speed reduction ratio, then we can make a robotic arm to become LTI system. Then we can apply this property of an LTI system, all right? Okay. After that, then you see here we have a diagonal matrix, diagonal matrix, diagonal matrix, okay? And the next slide is to help you to understand the multiplication among the diagonal matrix will result in the final diagonal matrix. So this is this one times this one times this one. Result will be again another diagonal matrix. All right. Diagonal matrix means what? So this block diagram actually is equal to a set of independent block diagram. So all of them are independent. So it means the first row is independent from the second row independent from the third row. Okay, so this is the mathematical meaning with diagonal matrix. All right, then this block diagram become an independent individual block diagram. So each individual block diagram is like this. Okay, so you have a scalar input, scalar output, and the inside you have this transfer function. All right. Then based on this result, then the question becomes how to design control system for each individual dynamic system under control. So we have an individual dynamic system under control. Then how to design a control system for it. Then this becomes a very simple problem. It's like you have a motor, you just treat this as a motor, how to design the feedback control loop for a motor. That's it. Okay. So the answer is step one, we start with the annular dynamics at the top joint. So this is the result at the top joint. Okay, you see. So then we want to move one step deeper to look at the result at the power joint. At the power joint, then we have a control signal. Then then you see we have an independent block diagram at the power joint. Okay, so then we produce top as output from the power joint. Then we can link them together in order to obtain the independent annual dynamics on the controller at the power joint. So here you see input is the control signal, at the power joint side. Then output is the motion parameter from the power joint. Okay, so then in front of it at the upstream of this signal flow, because this is 1/s, this is the integrator, then you should be able to see velocity. Then in the upstream of this transfer function, because this is 1/s, then you should be able to see acceleration. So therefore you have a position, velocity, acceleration. Okay, so this is a block diagram for each individual joint under control. Now we can lump all this together to have this simple representation. Okay, so you have a control signal as an input, then motion as the output. So let me call this the joint dynamics under control. We have n such dynamics under control, which are totally independent. Okay, so then actually these correspond to power joint, correspond to the actuator. All right. Then how to design the control loop? So it's very simple. Okay, so you just in sensory feedback, then bring it to the input side, then you compute the error, then supply the error to the PID controller. Then PID controller will calculate the value of the control signal, then supply this signal into the dynamics of a power joint under control. That's it. All right. If let's say you are going to do position control, then you can follow this design solution. Okay, so this is a design example for position control. If you want to undertake a velocity control, then this is a design example for velocity control. So you see, it's extremely simple. Okay, now I'm going to show you a practical example in industry. Okay, so in lecture 1 of module 4, you have an example which are similar to this one. Okay, so this is a position control of a DC motor. So you know this is a transfer function of a DC motor. Okay, between velocity as output and the torque as an input, because the torque is proportional to current. So this is why here I put the I here. Okay, so this is equivalent because because the torque equal to K times I. So that K, you can absorb the K inside this big K, all right, okay? So, and this one show you the PV controller. V means velocity. So basically, we can consider this one is a velocity controller, okay? So this one is something which replace this PID controller, okay? You just imagine this is a controller, actually. We call it as a PV controller. It's a proportional and the velocity controller, okay? Then this is a dynamics under control, okay? So this is dynamics about the position. Position is an output, velocity is an input, okay? So this is a special name, but for you no need to pay attention to this PV controller. You just consider this is the position control loop, which has an inner loop and the outer loop. So inner is a velocity control loop, outer is a position control loop. And the beauty of this design solution is to make use of error signal to serve as a desired velocity. So actually, this makes sense in physics. Okay, when the position error is very big, then we need to quickly converge or quickly reduce the error, John. Quickly reduce the error means what? Set the desired velocity to be very big. Then, okay, so it will quickly converge to zero. So therefore, we just use error in position to serve as a desired output from velocity control loop. When the distance becomes smaller, then this will be small. So it makes sense for us to slow down the speed or slow down the motion, John. Okay. So then when this error becomes small, desired value for velocity also small, then this will slow down. When this becomes zero, means what? Velocity must also become a zero. Then we stop at the exact location with the zero velocity. So you see the beauty of having these two summation in this order, okay? So position error equal to desired velocity output, all right? Then here, this is the inner velocity control loop, and here is a position. Basically, it's a position controller because we have a K here. You just imagine K is here. Then this is a P controller. So it's kind of PID controller. All right. So if you calculate the equivalent transfer function, first replace the inner loop by equivalent transfer function, then replace the outer loop by equivalent transfer function, you should be able to get this transfer function with omega n equal to this one, and the 2 zeta omega n equal to this one. All right. So this is a transfer function. Now you look at the design specification. Okay. So this robot actually will drive a different link. Okay. If there's a motor at the joint 1, we'll drive a 6 link, link 1, link 2, link 3 all the way. Then motor at the joint 5 will drive a 5 link. Motor at the joint 2 will drive a 5 link. Motor at the joint 3 will drive a 3 link. Motor at the joint 4 will drive a 2 link, etc. Okay, so that means different motor will have a different moment of payload, moment of inertia. So you can choose the value for J. J is the moment of inertia. Okay, so this is just an example. Then if you have a different, if you have a motor at a different joint, that means the moment of inertia for joint 1 should be very, very large. Okay, because this motor will drive a 6 link. All right. Okay. Now you see design specification is to have overshoot 20% and time at the overshoot equal to 1. Okay, overshoot means you have a first maximum overshoot and then time equal to 1. Okay, equal to 1. Based on these two design specification, it is good enough for us to determine K and the K hash. Okay, so you remember from a study of lecture 1 of module 4, then we have a formula for maximum overshoot. We also have a formula for the time of overshoot. Okay, so this formula basically depends on zeta. If we know this value, then we know this equality, then we can calculate zeta. Okay, then this formula depends on omega d. Omega d equal to omega n times the square root 1 minus zeta squared. Okay, so and if we know omega d, that means what? We know omega n. Once we know zeta, we know omega n. Then we know this final transfer function. Because this final transfer function has omega n equal to square root k divided by j. Then in this case, j equal to 1. Then we can calculate because we know omega n, then we know what we will know k, k equal to this one. And from this equality, since we know zeta, we know omega n, we know k, then we should be able to know k hash. So calculate k hash in this way. Done already. Okay. So we come out the design solution for this motor at the one particular joint inside your robot, right? And we can also verify what should be the rise time for this design solution. So you use this formula. So rise time, so it's equal to this one. And okay, here you see in the formula for rise time, you need to know what is the beta. So beta anyway, they give you this equation. Okay, so and then you can calculate the rise time. Okay, so you follow the formula of the design specification, so you should be able to determine the rise time. Then in this case, the rise time is equal to the time when the output first reach the steady state response. Because we may have another definition of a rise time, which is the time taken by the output when it goes from 10% to 90%. Okay, but for this example, we follow this definition: that rise time equal to the time when the output reach the steady state response at the first time. All right. Then for settling time, okay. So if let's say we define 2% of error band, then you use this formula. If you define 5% error band, then you use this formula. That's it. Okay. So you see, so this example basically show you the design of a control loop at the power joint level. Okay. If we can make a robotic arm to behave like a LTI system, then MIMO become a SISO. Okay, then we have an independent control system for each joint inside your robotic arm. Okay, then this slide show you some video. So basically, you should be able to apply the learned knowledge to achieve all these results in future. All right. So that's all for today's lecture. The key takeaway from today's study is to know the design solution for the control of a robot with known dynamics, and also the control solution or design solution to the control of a robot with unknown dynamics. Then with this knowledge, you should be able to implement the control system for your future robot. Thank you for your attention. I'm looking forward to seeing you in the study of lecture 5. of module 4.